Are you guys seeing this thing that says ionic nomenclature?
Hmm.
Okay, so the nomenclature that we did before just used those prefixes to discuss what substances were in the compound, like sulfur trioxide, that there was a sulfur there and three oxygens. And that was for covalent nomenclature, which is significantly easier than ionic nomenclature. So for ionic nomenclature, the rules are definitely different, and you need to be able to recognize when you're using covalent and when you're using ionic, and then also when you're using acid-base nomenclature. So do you know how to identify the fact that all of these molecules up here either get named via ionic nomenclature or acid-base nomenclature? Take that as a no. When we're looking at covalent compounds, the covalent compounds are only made between nonmetals and nonmetals. So when you look on the periodic table, there's that stair step thing on the right-hand side. Anything that's on the right-hand side making a bond with anything that's on the same side, that right side, that's a covalent molecule. And so you use covalent nomenclature. So in the ionic nomenclature, you've got ions. It's a cation and an anion come together. And usually what that means is there's a metal, so something from the left side of the periodic table reacting with something on the right side of the periodic table. And so when you look at this list, these first 10 here, you should be able to look and say, hey, that's a calcium. Calcium is a metal. So this is an ionic compound. So I have to use ionic nomenclature. You also could have said, hey, that's the polyatomic ion carbonate. So this is that means it's an ionic substance because that's a polyatomic ion. So can you name that first compound, that CaCO3? Are you there yet? Becca, Deanna, anybody?
No, but I did order the table of elements shower curtain. It should be arriving soon. I'm pretty excited about it. Yeah.
That sounds like something I would order. And then
Well, we had shower doors the last time, so I was like, I might as well be staring at this.
anywhere you can do learning, lifelong learner. All right, so this first one up here, you look at this and you say, hey, there's a calcium there, so that's an ionic substance. All right, so then this is calcium, so you just say calcium. And then you're supposed to, you need to recognize that that's one of the polyatomic ions. It's on the list of polyatomic ions to know. And so then that's a carbonate. So anytime there's a CO3, then that's got a -2 charge on it because that's the way that particular polyatomic ion works. And so then you'd know that that charge was -2. So that the list of polyatomic ions I'm talking about is on page 220. It's table 5.7. And so those are polyatomic ions you should be familiar with so you can name different structures that you come across in the book and homework and on the exam. There's only 11 of them up there. So there's a little bit different situation between number 1 and number 2. When you look on the periodic table, you're going to find that elements that are in the first and second column have fixed oxidation states. So that means that their charges never change. So when calcium goes into a molecule, it always has a +2 charge. And so since it always has a +2 charge, you don't have to tell me it always has a +2 charge. But the substances that are in the transition metal area, which is that depressed section on the table that's between scandium and over to zinc, all of those below there, they all have variable oxidation states, or almost all of them have variable oxidation states. Well, iron is there, and so that means you would need to be able to tell me what's going on with the iron. So I'm going to stop sharing this thing and switch over to a dry erase or a erase whiteboard. So the compound that we had on that other table was FeO. So when I make a compound, what ends up happening is for the ionic substances, so an ionic substance is cations, positively charged things, and negatively charged things, and they form a compound together because the positives and the negatives cancel each other out. So all molecules have a zero overall net charge. So the best, easiest example of this is, that's table salt. So why is table salt's formula NaCl? Well, whenever sodium forms a molecule, it always loses one electron, so its charge is +1, and chlorines like to be a -1 charge. So then the ratio for this compound is just 1 sodium and 1 chloride, because the +1 and the -1 cancel out. And that's what we're always trying to get to, that this, whatever this charge here is and whatever this charge is here, they cancel out. So to make it a little bit more interesting, I'm going to say that the formula for magnesium chloride, instead of sodium chloride, magnesium chloride, this is the formula.
Mhm.
So can you tell me why I need 2 chlorines?
Does magnesium have, okay, so it's 2 negative charges, right?
Yep, I've got,
Magnesium must have 2 positive ones.
so this is a chlorine with a -1 charge and a second chlorine with a -1 charge. And so you're right, then that the magnesium has a +2 charge. You would know that if you looked on the periodic table, you would see that magnesium is in the second column, and everybody in that column, when they form a compound, they always form +2. So the reason that this is MgCl2 is because there's two -1 and -1 there for the 2 chlorines, and this guy is a +2. So all of that stuff cancels out, and so we end up with just MgCl2. Does that make sense?
Mm-hmm.
All right, so oxygens are almost always -2 based off their position on the periodic table. So in this compound, what's the iron's charge?
+2.
Yeah. Okay, so there's an issue with iron. Iron can either have a +2 charge or it can have a +3 charge. So in this compound, it's got a +2 charge. But because it has multiple options, more than one option, you have to tell me what its charge is when you're telling me what molecule it is. So you might want to say that this molecule that we're looking at is called iron oxide. And if you said that to me, I would have to say back to you which one. I would have to say which one because there's this version of it too, iron with a +3. And if it's iron with a +3, then if this guy's a +3 charge, but the oxygens are a -2 charge, how do I get them to cancel out to be 0 overall?
You add 1 oxygen.
Okay, so if I put another oxygen on, now I've got another -2 charge.
Oh gosh. Okay, wait. So we would have to add. So we would need to get. We needed to get to 6. So we would need 2 of the irons and then 3 of the oxygens.
So what's it called, that thing that you just did in your head?
Balancing the formula.
No, when you said we need to get to 6.
You're multiplying.
Yeah.
I don't know.
Common denominator.
Yeah.
Okay.
Least common multiple.
Mhm.
Not the common denominator, but the least common multiple. So the two things that both of those would divide into evenly, or would be able to divide into. So in this case, it's 6. So you're right. We needed to get to +6 and -6 to get everything to cancel out. So the formula for this is Fe2O3. So you have these two possible compounds with iron and oxygen. So if you had this compound right here and you just said iron oxide, why is that bad?
Because it doesn't balance out.
No, it does balance out.
Because if you do 2 or 3.
Specify if it's balanced out or not.
Well, that's not the issue. The issue is, what would you call this one over here on the right? It's iron and oxygen. You can't call them both iron oxide. So what you do is you see this is an oxygen with a -2 charge, and then you identify that this iron's +2. So you actually say iron 2 oxide.
Okay.
So what do you do over here?
Iron 3 oxide.
Yep, that's it. Iron 3 oxide. So why do I have to differentiate between these two things? Why can't I just use the same name? This one right here the Fe2O3, that's rust. Just straight up normal rust. This one over here is technically another kind of rust. It's not just the regular rust that you see. This only happens under specific conditions. You have to have the right temperature and you have to have the right pressure, and then you can make this rust. So tell me what's bad about just regular rust. This guy over here, the one you normally see.
Hmm.
It really only has one bad property. So why don't you like things to rust?
It corrodes them, right?
Okay,
It
so
makes them more fragile and more likely to fall apart.
all right, that's it. When the substance rusts, so the surface of the iron rusts, then the rust falls off. That's the crux of it. So because regular rust, regular iron 3 oxide, it does not stick to the underlying iron, then that stuff is bad because it flakes off and then that exposes the iron underneath so it can rust. And when you're finished with it, you've got a bunch of rust and you don't have a structurally sound material anymore. So this one over here is completely different. When you have iron 2 oxide, that rust adheres to the iron that it was connected to before. So what's not going to happen to the iron underneath it?
It's not going to corrode.
It's not going to corrode. It's basically like you use the iron to paint itself. And so once the paint's on there, then not until the paint gets chipped off will that start to rust. Well, this stuff is really good at not letting anything chip it off. Do you know what powder coating is?
Mm-mm.
It's just this way to basically bake on a paint-like material. People will do it to mountain bikes or bumpers. It's kind of like Rhino Liner, but not, because Rhino Liner is really just an adhesive. But in the end, you get the same kind of effect. You can like beat on it and whatnot, and it just doesn't let go of the iron underneath. So if you're going to build a nuclear power plant and you don't want your pipes to rust, you do this to the pipes, the inside of the pipes. And then you don't have to worry about them rusting because the iron 2 oxide doesn't come off. So are iron 2 oxide and iron 3 oxide different?
Yes.
Oh yeah. So that's why I have to say either iron 2 or iron 3 oxide, because then it tells me what the substance is. So when we get back to this, and I'm trying to figure out names for substances, so let's do CuSO4. All right, so this is this guy here, this SO4. This is one of the polyatomic ions that is in the book that you're supposed to know what it is. And so this guy is a sulfate, and the sulfate's charge is -2. All right. So this compound here is, since you don't see any charges, that means it's a neutral compound. That means that's how it's supposed to be. So what's the charge on the copper got to be?
8.
No. This whole thing, this whole guy right here, this sulfates, the entire sulfate's charge is plus or -2.
Oh, so it'd be +2.
It'd be +2. That's it. So this thing has a +2 charge, and this thing has a -2 charge. And copper is in that transition metal area. So that means that you need to tell me what its charge is, because it has more than one option. So what would you name this?
Copper 2 sulfide?
Sulfate. Because that thing right there is sulfate. But yeah, copper 2 sulfate. So what about this one?
Magnesium coating?
There's one difference here. Magnesium does have a +2 charge. You know that because you already knew the sulfate has a -2 charge, and so they just cancel each other out. But you don't say magnesium 2. How come? Why did I have to say copper 2 and iron 2?
It's not transitional. Magnesium?
It's not one of the transitional metals, so it doesn't have a variable oxidation state. So that means its charge is always +2, so you don't have to tell me its charge is +2. Just like on that first one we looked at with the calcium and the carbonate, that its charge was, the calcium's charge is +2, and that's because those guys are both in the same column. But because their charges are fixed, you don't have to tell me what the charge is. So, the first thing we looked at was that. And so what's this thing's name?
Sodium chloride?
Okay, but you don't need to say sodium 1 chloride because sodium's charge is always +1 in a compound. So what would this substance's name be?
Oh, what is K?
Potassium chloride?
Yep, sodium is right above potassium on the periodic table, so they both have the same charge. So that means the potassium's charge is +1, and so I just need one of each of them to go to cancel out their charges, because if this guy's a +1, and we already knew that the chlorine is a -1, then the charges neutralize each other, and we just end up with potassium chloride. And I don't need to say potassium 1 chloride, because potassium's charge is always +1 in a compound.
So if it's implied, just don't bother.
I'm sorry?
I said, so if it's implied, you don't need to bother with it. It's only stuff like iron, which you don't know for sure.
Correct. If it can't be anything other than a +1 or a +2 or a +3, then you don't tell me. But if it can be something other than the charge that it's at, then you have to tell me. Because like CuCl2 and CuCl are two totally different compounds. They look very similar, but they're very, very different. So what's the name of the first one? This is copper, right?
I was looking for, because I downloaded and I printed out a list of the elements and what they actually are on the thing, but I can't find it.
Yep, it's copper.
Okay, copper.
So Cu is copper, and then the Cl is chlorine, and we already know that this chlorine's charge is what?
2.
No,
Oh, 6, sorry.
the chlorine's charge are -1. So remember this up here, the sodium chloride was just one of each, and the potassium chloride one of each.
Mhm.
So how many negative ones are here?
2.
Okay, so that means that's -2 total. So what's this copper have to be?
Composed of 4.
No,
+2.
+2 total.
Okay.
So this copper is a +2. Each of these chlorines is a -1. And so how about down here? This chlorine's charge is still a -1. So what's this copper's charge?
Positive.
+1. So this one here, this is copper 2 chloride, where this one down here is just copper 1 chloride. Again, different substances, so they need different names because they have different properties. So how big a difference can their properties be? Well, you know what that is. What's this?
The hydrogen dioxide?
No. I mean, technically that would be a good name for it, but you know it as another thing. This is hydrogen peroxide.
Oh.
Do these things have different properties?
Yes.
What happens if you drink hydrogen peroxide?
It makes you vomit.
Immediately. You vomit immediately. Like,
Yeah.
it gets in, a second it hits your stomach's like, nope, none of that, and you throw it up. So,
We had a dog that ate chocolate hydrogen peroxide one time.
yep, same thing with me. I went out to the drugstore looking for that syrup of Icapec stuff, and they don't sell it anymore. And they're like, just a cap full of hydrogen peroxide, and bam, there was 10 ounces of chocolate on the ground.
Yep.
So they have different properties, right?
Yeah.
So you definitely need to use different names for them. And so that same situation happens with copper that's got a 2 charge and copper that's got a 1 charge. They need different names because they're different things and they have different properties. Does that make sense?
Mhm.
Okay. So let's do. So how about what's the name for number 4? Or let's do number 16.
Potassium chloride.
PB is lead.
Oh.
K is
Well, no.
potassium. Lead has a variable oxidation state, so you can't just say lead.
Oh, okay.
So what are you going to say for this one?
Lead 2 chlorine.
Almost right. What was wrong with that?
Chloride.
You always end the names of the elements in ionic compounds or any actually compounds with "ide." Like, what's the name for CO2?
Carbon dioxide.
So it always ends in "ide" as opposed to carbon dioxygen.
Mhm.
Okay, so how about 14?
Aluminum chloride. Oh, is aluminum 3 chloride?
Nope,
Nope. Oh, that doesn't vary.
it doesn't vary. It's not in that transition metal section. So you just say aluminum chloride. So my question now is, how are you supposed to know that if I gave you aluminum chloride as a name, how do you get back to AlCl3? When you read aluminum chloride, how come it's not just AlCl? What's the charge that the chlorine makes?
-1.
Okay, so if the chlorine's charge is a -1, and what's the aluminum's charge going to be?
3.
+3. So how do I get, what's the least common multiple now between 3 and 1?
3.
3. So the aluminum's already there. So that means I need 3 separate -1 chlorines to cancel out my +3 aluminum. So that's how we get to AlCl3. So if you've got this name here on 25, magnesium chloride, how do you come up with the formula?
The charges.
Okay, so you already know the chlorine's charge is a -1. Okay, so whatever happens, I know that chlorine is going to be a -1. What's the magnesium's charge? Well, you find magnesium on the periodic table. You see it's element number 12, and it's in column number 2. And so elements in column number 2 all have a +2 charge. So what is the formula you need to put those two together?
Mg. 2.
Yep, that's it. Does that make sense, Deanna?
Yeah.
Okay.
I think this is going to get a lot easier once I have the periodic table memorized, or more. I'm working on it.
How about 46? So you don't know the lead's charge because it's variable, but what's the oxygen's charge been?
+1? No.
Nope.
-1.
Nope.
Okay.
2.
-2.
Mm.
So if the oxygen's charge is -2, and there are 2 oxygens in this, then what's the charge on the lead?
4. Positive 4.
Yep. So what's the name of this?
Lead 4 oxide.
Lead 4 oxide. That's it. And yeah, you do need to remember you're talking about Roman numerals, so that's what a 4 is.
Mhm.
Let me get down to the bottom here. So here's a little periodic table that I came up with, and then I put this first column, everybody's a +1, and then the second column, everybody's a +2, and then I'm skipping over all of these, all the transition metals, until I get over to boron, and so +3, and then the carbons are plus or minus 4, and then the nitrogens are -3, and the oxygen column is -2, and the fluorine column is -1, and the last column doesn't do any reacting, so you don't need oxidation state for that.
Okay, don't take that away. I'm taking a picture of it. There we go.
Okay.
Thanks.
So what you're trying to do is when you're putting things on this side of the table over here together with stuff on this side of the table, then you need to make sure that their charges end up equaling 0. So based off of what I just said, what would the formula be for beryllium, which is Be, making a compound with sulfur, which is S?
It's SAS? Sorry.
S.
S. Okay. It would be balanced.
So what would the formula be?
It would be BeS2.
No.
No.
The sulfur's charge is -2, right?
Mm-hmm.
So if you had 2 of them, then that would mean you had -4 total.
Okay.
And you only have +2 with the beryllium. So what's the formula?
BES.
That's it, BES. End of story. What about if you reacted it with the beryllium with selenium, which is element number 34?
Same thing.
BESE, right?
BESE. Yeah.
What about tellurium, which is element number 52?
BETE.
Yep, that's it. So what happens if I try to make a formula with beryllium and bromine? BR, 35.
Okay. It would.
BeBr2.
Yep. Because the berylliums are still a +2, but now my anion, my bromine, only has a -1 charge. So I can't just put 1 on because it doesn't fully cancel out the +2 charge. I need to add a second one with a -1 charge to fully cancel out the +2 charge. So what's the formula with beryllium and iodine, element 53?
BeI2.
Yeah. And beryllium and chlorine?
BeCl2.
Yep. So anytime beryllium is going to make a compound with anybody in that second to last column, the one with the fluorine at the top, it's always going to be Be and then whatever the element is with a 2. So it's BeF2, BeCl2, BeR2, and BeI2. So since beryllium and magnesium are in the same column, that means they have the same charge. So what's going to happen when magnesium makes a compound with iodine? Number 53.
Same thing. BeI2.
Yep, and that's how you use the periodic table. You can figure out what formulas are going to be based off of knowing what the entire column's charge is going to be. So then if I mix anything with column 2 with anything from column 17, I have one thing from column 2 and 2 of those things from column 17. Does that make sense?
Yeah.
So what is it if I mix anything from column 1 with anything from column 17?
One of each.
Yep. What happens if I mix anything from column 1 with stuff from column 16?
Two things from column 1, one thing from column 16.
Yep. So if I mix, say, lithium, element number 3, with oxygen, element number 8, the lithiums are both +1. All lithiums have a +1 charge, but the oxygen needs to be a -2. So I can't just put one lithium on because that would only cancel out one of the negatives. So if I put 2 +1 lithiums on, then I cancel out my oxygen that's got a -2 charge on it. And that's going to be the same for every element in column 1 with every element in column 16. So those ones are easy, but when I move to the transition metals, it doesn't work out so well because I have to look at the anions charge and then figure out what the cations charge is, like we did before. So I can't just say what happens when I mix nickel with chlorine. You have to give me more information. I would have to say, what happens if we mix nickel with a +2 charge with chlorines? Then you'd say, well, okay, the nickel's got a +2 charge and chlorines are a -1 charge, so it needs to be 1 nickel and 2 chlorines to cancel out. But you have to be told that the nickel's charge is going to be a +2 because it could be a +3. So you need to be informed. Does that make sense?
Mm-hmm.
Okay.
I totally had an epiphany moment during all of that, so that was nice. I was like, oh, I get it.
Good. Those are always fun.
Yeah.
Okay. What else you guys want to talk about?
Can't think of anything right now.